Good afternoon, students. So our next lab experiment is analog to digital converter. So today's lab class, we are going to see about how to interface 8051 with 0808 ADC, okay, analog to digital converter. So interfacing 8051 microcontroller with ADC 0808 is our today's experiment. So most modern microcontrollers with 8051 IP cores have an inbuilt ADC. Okay, most of the recent microcontrollers, 8051 IP cores microcontroller, have an inbuilt ADC. So the older versions of 8051 like MCS51 and 8089C51. So these microcontrollers don't have an on-chip ADC. So therefore, we have to connect these microcontroller to analog sensors. Suppose if you want to interface analog sensors with microcontroller, so that situation the microcontrollers needs to be interfaced with ADC. Okay. So what is the purpose of this ADC? Why it is necessary? Why we are converting analog to digital converters? Converting analog data to digital data. So what is the necessity of converting analog to digital? For digital processing to get accurate value. Any other answer? Everything can be represented in ones and zeros. The environment, that is the right answer. The environment around is maximum analog. Okay. So any microcontroller can process the physical parameters such as temperature, pressure, speed, and torque. Okay. So these parameters are sensed by sensors. So what is the purpose of sensor? What is sensor? So can anyone unmute and tell me the answer? What is sensor? So sensors are transducers that convert a physical parameters like temperature into electrical signal so that the microcontroller can understand. Okay. But here the problem is analog sensor output the data in the form of analog format. So which microcontroller cannot understand. So therefore to convert this analog data to digital format, analog to digital converters are used. So that is the reason why we are interfacing ADC with 8051. The main reason is all your analog sensor will generate analog format. So that format your microcontroller cannot understand. So in between, we need some interfacing IC to convert analog data into digital. Okay. So the purpose of this ADC IC converts analog signal to digital. And here there are different conversion techniques for the conversion of analog signal to digital signal like flash converter, successive approximation, and dual slope integration technique. So these are most popular techniques used in the integrated ADC chips. Okay. So we are not going to talk about the different types of ADC, and that is not the focus of this experiment. Rather, we will talk about how the conversion happens from analog to digital value. Okay. And also we will write the program, that is assembly program, and compile it in the MCU8051 IDE. Subsequently, use Proteus to demonstrate the working of ADC. Okay. So the important parameter involved in ADC is step size. Any idea about step size of the ADC? So step size means that is the minimum change that an ADC can detect is known as step size of the ADC. Okay. So to calculate it, we can use this formula. Step size is equal to V max minus V minimum divided by 2 power of n. For example, the maximum voltage is 5, minimum voltage is 0. Okay. So this n is representing number of bit resolution of ADC. So this is nothing but your size of your ADC. For example, let's take 8 bit. So 2 power of 8. Okay. So 5 divided by 256. What is the answer? Please tell me. 5 divided by 256. What is the answer? So in order to calculate, what is the answer?
0.0153.
In terms of millivolt, in terms of millivolt, 19.53, I think so. Please find out.
Yes, ma'am.
19.53 millivolt. So in order to calculate step size, this is the formula. It's a very important parameter of your ADC IC. V max minus V minimum divided by 2 power n. N is nothing but your size of your analog to digital converter IC. So maximum voltage, let's assume 5, minimum voltage 0 divided by 2 power 8. So 5 divided by 256, you will be getting 19.53. So the inference is here. So your ADC can detect the minimum of 19.53 millivolt change. So that is the inference of this value. So that is the significance of this value. So your ADC can detect the minimum voltage change, that is 19.53 minimum voltage change it can detect. Okay, is that clear? So next we will move on to IC details. So ADC0808 is a popular 8-bit ADC with the step size of 19.53 millivolt. So the important thing is it does not have an internal clock pulse, that is internal clock. So it doesn't have internal clock. So designer has to supply clock pulses to this particular IC. So therefore it requires a clock signal from an external source. Okay, here we have to connect external source. So it is 28-pin IC. So it has 8 inputs, 8 analog inputs from 0 to 7. Here IN0 to IN7. Okay, but only one of them can be selected at a time because it has 8 digital output pins, D0 to D7. So here DB0 to, here DB3 is here, DB1, DB2 and DB0 to DB7. Okay, so it has 8 input pins, but only one of them can be selected at a time because it has 8 digital output pins. Only one byte it can accommodate. So it uses the principle of successive approximation for calculating digital value, which is a very accurate method. And let's look at the pin description to get more insights into ADC 0808. Okay. So first thing is input pin, that is IN0 to IN7. So it has 8 input analog pins. These pins are multiplexed together. So these pins are multiplexed together and only one of them can be selected using 3 select lines. We have 3 select lines here, A, B, C. So it has three select lines, namely A, B, C, that are used to select your input pins. So here important pin is associated with this channel selection is ALE. Okay. So this is the table. In order to select the channel 1, okay, consider this is channel 0 to channel 7. This is the select line information 000 IN1 is selected 010 IN2 likewise 111 IN7 will be selected. So in order to latch the address, ALE pin is associated with this channel selection. So ALE pin also needs to be activated by high to low pulse to select a particular input. So in order to select a particular input, we have to apply high to low pulse to this address latch enable in order to latch this particular information. Okay. So this is about input pins, address selection, and the address is latched into ADC based on this ALE signal. Okay. And next VCC ground. VCC ground. Here. VCC ground. So clock, as mentioned earlier, it does not have an internal clock, needs an external clock signal to operate. And V reference, positive V reference and negative V reference. So these two pins are used to provide upper and lower limit of the voltages, which determine the step size for the conversion. Okay. So your V reference has higher voltage value. So higher value, and your V minus reference minus has the lower voltage value. So already I have explained, if the V reference plus 5 voltage, V reference minus 0 voltage means your step size is going to be 15.53. 15.53 or 19.53? 19.53. Okay. So next, regarding your control signals, we have three important control signal. One is start conversion, another one is the end of conversion, third one is the output enable. So start conversion, so this pin is used to tell the ADC to start the conversion process. Okay. So when the ADC receives high to low pulse on this pin, it starts converting the analog voltage on the selected pin to its 8-bit digital equivalent. Okay. So in order to initiate the conversion process, we have to send high to low pulse to this particular start conversion pin. And next, end of conversion, once the conversion is complete, the ADC sends high to low pulse to microcontroller. So it will send high to low pulse to the microcontroller. That is conversion, to tell the microcontroller that the conversion process is completed and it can extract the data from the 8-bit data pins. Okay. So main thing is ALE is for latching your channel address information. Start conversion is for to initiate your conversion process, and parallelly, if the conversion is over, end of conversion is high to indicate that the conversion process is completed. And third signal is about output enable. So this pin is used to extract the data from the ADC. So after conversion, your data will be available from D0 to D7. Okay. So once the conversion process is over, so this output enabled signal should be activated to extract the data from D0 to D7. So these are the pins associated with your ADC IC, that is 0808. Okay. So we have totally 28 pins and 8 input pins and 8 output pins. So we can connect 8 devices at the input side, but only one device can be interfaced with your ADC. And this selection can be done by using this ABC address lines. So the particular address of this channel is latched into this IC using this address latch enabled signal, and start conversion is used to initiate the conversion process, and end conversion to indicate that the conversion process is over. After that, this output enable signal is used to extract the data, converted data available from D0 to D7. So these are the components required to design your ADC interfacing with 8051 microcontroller. So first component is 8051 microcontroller and analog to digital converter IC and 8 LEDs. This should be connected to your output port to extract your output data, and power supply is required, and crystal oscillator is for your microcontroller, that is for getting the clock pulses. This circuit, this microcontroller requires external crystal. So we have to supply clock pulses to microcontroller and some of the resistor, capacitors and DC voltmeter to measure your analog voltage. So these are the components are required. So this diagram represents the internal working of your ADC0808. Actually here V in is the input voltage. Okay, so that needs to be converted into digital value. Okay, so this input voltage is supposed to convert it to a digital value. So digital values are stored in this particular line, that is D0 to D7. So D0 to D7 are digital outputs that are obtaining here. So now how conversion happens is, so V in is supplied to the comparator. So this is the comparator. So it will compare input voltage and output of this component. Okay. So V in is supplied to the comparator, and the comparator output will control this counter operation. Okay, and the counter operation is incrementing operation. Okay, so let's see about the control signals involved in ADC process. Three signals. One is clock, start and end of conversion. Okay, suppose I want to start a conversion. That time the start of conversion pulse is provided to the converter. Provided to the counter. Subsequently, for every clock ticks, counter is going to be, that is going to get incremented. So the operation of this counter is incrementing. So after applying one clock pulse, this value is gets incremented. Okay. So every clock ticks, the counter is going to get incremented. So the operation is the incrementing operation. Okay. So counter will start counting for every clock pulses. Okay. So now this particular counter output, which is in digital form. Okay. So first thing, we applied the start conversion. So based on the clock pulse, the counter value gets incremented and parallelly it will generate digital outputs. Okay. So this particular counter output, which is in digital form, that is given to your digital to analog converter. Okay. And output of this DAC is analog here. Okay. So this output of this DAC is analog form. It is compared with V in value. Okay. So V in is compared with DAC output. So every time, first your process is initiated by applying this start pulse. Once your counter gets started, it start incrementing based on your clock pulse, and output will be generated here. So these are the output lines. So the output of the counter will be fed into digital to analog converter. So the output of this block is analog, and this analog value is compared with your input voltage. Okay. So the here comparison, when counter output, that is your analog output, exceeds Vn. This analog output so two condition. So whether this comparator will check whether this V in is check lesser than analog output or greater than analog output. So it's going to check three condition. Suppose if V in is greater than counter output. Okay. So that case, so first condition, V in is greater than your analog output. So that case, the counter will be incremented again because your comparator sends high output. When Vn is greater than analog output, the comparator sends high output, which will enable the counter to count further. Okay, so counting operation will be proceeded because your comparator generates high pulse to your counter. Okay, for the condition when Vin is greater than analog. Suppose your Vin is less than analog output, that case it will generate low signal, which will stop the counter. Okay, stop the counter for further incrementing. So that is the operation here. Okay, so first your conversion process is initiated by sending start signal. So after receiving this, counter will start incrementing the clock pulses. At the same time, it will generate digital inputs, and this block is used to convert this digital inputs into analog, and every time that analog value is compared with your input. For example, input is 5 voltage. So every time this value is compared with 5 voltage. Suppose your input voltage is greater than this analog output, that case your comparator sends high output to the counter, which will enable to count further. Suppose if it is lesser, it will send low signal, which will enable which will stop the counter from further incrementing. So that case, your process is completed. At the same time, it is connected with your end of conversion. It will generate end of conversion signal to the microprocessor. So to indicate that the conversion process is completed. So this is the internal operation of your ADC 0808. Any doubts? So Vin is your analog input. So that analog input is compared with your output of DAC. So two condition, Vin is greater than analog means it will generate high clock pulse, okay, which will enable counter to count the operation further. That is to enable the counter to count the further operation, that is incrementing operation. Suppose if the Vin is less than analog value, okay, so that case your comparator sends low output, which will stop the counter from further incrementing. So that case your conversion process is completed. Any doubts? Any doubts, students? So next one is the timing diagram of your ADC. So this timing diagram becomes the critical factor of analyzing and writing the program for ADC. Okay. So it's a typical timing diagram corresponds to ADC 0808. So you can see here the clock are being provided to the counter. So the clocks are being provided to the counter, internal counter. Suppose if you want to start the counter, so you have to provide this start pulse. Okay, so the first step is you have to generate start pulse. So before you initiate the start pulse, there is something called ALE. So this will latch the address, that is latch the address and decide which analog channel is selected in ADC. So I have already explained. So channel selection is based on ABC address lines. Once the channel is selected and the address is latched into the ADC IC using this ALE signal. Okay, so there are total number of 8 channels. So the out of 8 channel using this ABC, we can select one. Okay. Suppose if you want to select the first channel, okay. So that case you have to provide the address of channel 000, 000. So this is the address of your channel 0. So this address should be latched into your ADC IC. Okay. So that is done by using ALE signal. So once the channel is selected, if you want to convert the analog value to digital, you have to initiate this start of conversion signal. Once SOC is started, your digital counter start incrementing and keeps on incrementing, and analog output is continuously compared with your VIN. So mainly the operation depends on two control signals, start signal and ALE. So once the channel 1 is selected, if you want to convert the analog value into digital, you have to provide the start conversion signal. Once the start conversion signal is initiated, your digital counter start incrementing and keeps on incrementing. And every time the analog output is continuously compared with VN. So in the moment VN becomes lesser, so VIN becomes lesser than the digital output. That time, your end of conversion is asserted high. Initially, becomes low for a particular time period. Once the conversion process is over, so this value becomes high. So end of conversion is asserted high to indicate the analog value is converted. So what is the next step? So now completely converted into digital value. Your input is completely converted into digital value. So at that time, counter will stop counting. And further to that, if you want to read the digital output, you have to enable this output enable signal. High, particular period, high, from high, low to high, and after that, high to low. Then only your using this output enable only, we can read the digital output from ADC to the microcontroller. Okay. So first step, selection of channel. Once select the channel, you need to make the ALE high and then low. Okay. And the same time, you have to send the start of conversion to counter. Okay. So it's your counter keeps on incrementing till end of conversion becomes high. Once the end of conversion becomes high, you have to enable output, that is output enable pin high, then low to read the data. So these are the steps involved in your ADC programming. So first step, channel selection. Second step, ALE signal to make your ALE high and low. And next, initiate your start of conversion and monitoring your end of conversion. When end of conversion becomes high, means the conversion process is completed. And after that, you have to enable output, enable pin high, then low to read the data. So these are the steps involved in your ADC programming. So first, select the required ADC channel using ABC pin. Okay. And next, send high pulse on ALE for latching the above selected channel. For example, channel 0 is selected means your ABC will be 000. So this information will be latched into your ADC using this ALE signal. Okay. And after that, send high pulse to start pin to reset your SAR inside your ADC IC. Again, you make ALE line low and make start line low. So first make ALE high, start pin high, and ALE low and start line low. And wait for end of conversion line goes high. So if it becomes high, make output enable high to bring the conversion of data on the data bus, read the ADC data, and again you make this OE low. and store the ADC data for further processing. So these are the steps involved. So main thing, channel selection. Next, make your ALE high, make your start pin high. After certain period of time, make your ALE line low, again start line low, and keep monitoring end of conversion process. If end of conversion is completed, if the line becomes high, and activate your OE line to read the converted data, okay? And after that, make OE line low. Any doubts? Regarding your timing diagram, that is very important. So timing diagram is very important to program ADC0808 IC. Any doubts, no? So let's have a look on Proteus circuit. So I have designed this circuit. So this circuit has got ADC 0808 and your microcontroller. So this is your IC is interfaced with 8051 microcontroller, okay? Please note down the connection details. Please note down the connection details. First, after that I will explain. So your output enable is connected to P3.0. So only for interfacing, your port 3 is completely utilized. So your output enable of ADC is connected to P3.0 and address latch enable is connected to P3.1. And for your channel selection, your address C, address B and address A are connected P3.2, P3.3 and 3.4 respectively. And start pin of ADC is connected to P3.5 and end of conversion is connected to P3.6. Okay. And we have 8 digital outputs in ADC. So that is connected to your P2.0 to P2.8. For giving analog voltage, I have used part which is connected between V reference positive and V reference negative. That is connected to your channel 0. So in order to visualize your digital outputs, 8 LEDs are connected to P1.72, that is P1.0 to P1.7. And external clock signal is connected to pin 10. So this is the connection mapping. Please note it down. Otherwise, you will not follow you cannot follow the coding part.
Ma'am.
Yes.
Ma'am, பெருசு பண்ண முடியுமா மேம்? ரொம்ப சின்னதா இருக்கு.
இல்ல பண்ண முடியல.
பண்ண முடியும். ஓகே.
So 3.0 is a write pin. Write pin means your microcontroller can send the values from 3.0 to ADC. From microcontroller to ADC is called write pin. Okay. So your microcontroller will write either 0 or 1 to P3.0. So read pin means the data from ADC, that is your ADC IC to microcontroller. Write pin means your data is transferred from microcontroller to ADC. So that is the difference. So all the pins are write pins. So your microcontroller can send the values from port 3.0 to 3.5 to your ADC IC. So all the pins are configured as write pin, and your 3.6 is end of conversion pin. It is configured as read pin. That is your data is transferred from ADC to microcontroller. So that is the difference. So here oscillator circuit. This is the oscillator circuit. So connect the oscillator circuit to pins 18 and 19. So actually this circuit includes crystal oscillator and two capacitors of 33 PF each. Okay. So connect these to the pins as given here, that is 19 to 18. Please note down the connection because you have to simulate this one. So you have to design this circuit and connect this crystal oscillator circuit to 18 and 19. Please note down the connections. So first we will see about the connections involved in 8051 microcontroller. So we are using port 2, okay? Port 2 as an input port, okay? So here I have connected output ports of ADC, output pins from out 1 to out 8. So all the output pins are connected to P2. Please note down the connections, okay? So as mentioned earlier, your ADC does not have an internal clock. So therefore we have to connect an external clock. So connect the external clock to pin number 10. So the clock sources are available in this option. Here you can select this one, either D pulse or D clock. So we have to connect an external clock pulse, okay? So here you can select your D clock. So connect this clock to pin number 10, okay? So 8 LEDs are being connected to your port 1 in order to view your converted value, digital value, okay? And here, so coming into this IC, we have two reference voltage, positive V reference and negative V reference. Okay, so these two pins are connected across your part. Okay, and this part is connected to your channel 0. Please look at the connection here. So I have connected this part to your channel 0. And this V reference positive and V reference negative will decide the step size of your ADC based on your maximum and minimum voltage. Okay, and address selection can be done by using add C, B, and C. Okay, and add A is connected to 3.4. Okay, and add B is connected to 3.3, and this is connected to 3.2. Okay. And next important signal, start conversion, end of conversion, and output enable. So end of conversion is connected to 3.6. It is a read pin. Okay. So signal is generated from ADC to microcontroller. If the pin is a right pin, the signal is transferred from 8051 to ADC. Okay. So output enable is connected to 3.0. So the logic here is initially we have to make ABC as 0 in order to select this IN0, channel 0, so that it selects the IN0, that is channel 1, IN0. If ABC has to be 0 means your P 3.4, 3.3 and 3.2 should be 0. So that is the meaning. Okay, so we have to pass 0 to ADC C, B and A. Means your channel 1 is selected. Okay. So once the channel is selected, we have to latch the address. So that is done by ALE. So which is ALE here? Where is ALE? So here. So we have to latch the address. So that is done by P3.1. So the address is provided by these 3 pins. That is your 3.4, 3.3 and 3.2. So once we have latched, next we have to start the conversion process using this SOC signal, start conversion signal. Once ADC completes the conversion, it will acknowledge using end of conversion. Okay, it will send end of conversion signal to microcontroller. So further end of conversion is received. We have to make OE is equal to 1. OE is equal to 1 to make the ADC to provide digital equivalent of analog value. Okay, so that will be available on your out 1 to out 8. Okay, so these pins are connected to P2. So converted data will be available in P2. Okay. So here your input is provided by your part. So based on the input voltage, your ADC will convert the analog value. That converted value will be available on P2. Okay. So further, we will transfer that value into P1.0 to 1.7. Based on that, respective LED will glow. Okay. So this is the circuit logic involved in the Proteus. So next, we will move on to coding part. Any doubts up to this? Yes, Balaminakshi.
And why we are using that capacitor crystal
That is a default circuit. For filtering, actually pre-scaler circuit, no, 8051 supports scaling for converting high frequency pulses to low frequency. For that case, we have to connect capacitance because your frequency is internally divided by 12. So your capacitance will take care of converting your high frequency to low frequency.
Yes, ma'am.
So it's a default circuit. We have to follow that to generate 12 megahertz frequency. Yeah.
Yes.
Any other doubts? So what is the steps involved? What are the steps involved? What is the first step? Please tell me. What is the first step?
Ma'am, we have to make port P32, P33 and P3.4 to 0, ma'am.
Okay. What is the next step? After that, after selecting your channel, you have to latch your address. Okay. So what is the next step?
Ma'am, and P3.1 we have to initialize to latch the address.
Very good. Next.
And then P3.6, we have to initialize, we have to make it as 0, ma'am.
Okay.
And after that, we have to initialize P3.0 to 1, ma'am.
Okay.
Uh, I think, and after that, we'll get the digital value, no, ma'am.
For that, we have to monitor end of conversion. What end of conversion is connected to which pin? P3.6. Okay.
P3.0, ma'am.
So we have to continuously monitor P3.6. Okay.
Yes, ma'am.
Okay. So let's focus on the writing the program. So all the output lines of your ADC are connected to P2. Okay. So we have to configure P2 as input port. Okay. So the first step is move P2, comma, hash 0F.
Ma'am, your screen is not visible, ma'am.
1 second. Is it visible now?
Yes, ma'am.
Okay. So first you have to make P2 as input port. Okay. So for that, write 0FF to P2. So that is the first step. And next, so what is the purpose of this instruction? Set bit P3.6. What is your P3.6 here? Students, please tell me. What is P3.6?
End of conversion.
Okay. So what is the purpose of set bit P3.6? Because it is a read pin. So we have to configure this particular pin as an input pin. Okay. So your end of conversion signal will be generated by ADC. Okay. And your end of conversion is connected to P3.6. So this pin should be configured as input port pin. Okay. So set bit P3.6 is nothing but to configure end of conversion pin as an input pin. Okay. Please note it down. And next, clear the data lines which are connected to the pins ALE, start and output enable, because as all these pins require high to low pulse to get activated. Okay. What are the pins? Address latch enable. Initially, we have to clear all this. Address latch enable, start and OE. Okay. So next instruction, clear P3.1, clear ALE. Okay. Next, clear P3.0, clear output enable pin. Okay. Next, clear P3.5, clear start pin. So these data lines should be clear because these pins require high to low pulse to get activated. So initially these pins, these data lines have to be cleared. Okay. So next step is the main step. We have to select our channel. So what are the pins are associated with channel selection? Your 3.2, 3.3 and 3.4. Okay. So here I have chosen your channel 0. So I have to clear all your pins 3.2, 3.3 and 3.4. So clear P3.2. Next, clear P3.3. Next, clear P3.4. So this is for your address line C, B, A. Now your channel 0 was selected. Okay. So next, what is the next step? What is this next step after the channel selection? What is the next step? So we have to latch this address. So once we have done this, next step, your ALE has to be high. Okay. So what is the pin associated with your ALE? Please tell me.
3.1, ma'am.
1. Okay. Next one is state bit P 3.1. In order to generate your ALE signal to latch the channel address. Okay. And after that, you call delay. Okay. Next, initiate the conversion process. Set bit P 3.5. Start of conversion. So your ALE is enabled, start of conversion is enabled. Okay. So what is the next one? So your ALE requires high to low pulse. Similarly, your start pin requires high to low pulse. So set bit instruction is used to make the pin 3.1 as high. Similarly, P 3.5 as high. So what is the next step? So make start pin low, make ALE low. So that is the next step. So first step, ALE has to be high and then start has to be high. And after that, next ALE should be low, then start of conversion should be low. Okay. So A call delay, set bit 3.5 again. A call delay. Clear P 3.1. So this instruction is used to make your ALE low and next clear P 3.5. So please look at this timing diagram. So I have simulated this part. So I have simulated this part. So ALE high, after that start pin high, okay. Next ALE low, start pin low.
Your screen is not visible, ma'am.
ஷேரிங் இருக்கு இருக்கு
விசிபிளா இருக்கு மேம்.
விசிபிளா தான் இருக்கு இங்க
okay.
ஷேரிங் ஸ்கிரீன் வருது லைனா தனலட்சுமி தெரியுதா
தெரியுது மேம்.
ஓகே So first ALE high, next start high. After some time, make your ALE low and start low. Okay. So these instructions are used to select your channel and also initiate your start of conversion. Okay. ALE high, start high. ALE low, start low. Okay. So what is the next step? So once the conversion process is initiated, what would be the next step? So what would be the next step? Students, please tell me. So So what is the next step? So your conversion process is initiated now. So we have to monitor
The counter reading, ma'am.
we have to monitor end of conversion. Your microcontroller will continuously monitor end of conversion signal. So here you have to incorporate jump bit P3.6 L1. So wait this particular instruction till end of conversion becomes low. According to this timing diagram, initially it is high. Okay. So we have to wait until this end of conversion becomes low. Okay. So next step, jump no bit P3.6 L2 here L2. So wait here till end of conversion becomes high. So according to this timing diagram, so we have to wait until EOC becomes low. Similarly, after some time, we have to monitor this end of conversion becomes high. If suppose if this end of conversion becomes high, the conversion process is completed. Okay, is that clear? See, we have to wait till end of conversion to become 0. For that case, we are using this jump bit instruction. So this will monitor end of conversion is equal to 0 or 1. Okay. If it is 1 means the instruction will be repeated again and again. Okay. If end of conversion is equal to 0 means it will execute the next instruction. So what is the next instruction? Again, it will monitor end of conversion signal is 0 or 1. Suppose your end of conversion is equal to 0 means again this instruction will be executed. Otherwise, it will execute the next instruction. Is that clear? So just you refer this waveform. Initially, your end of conversion is high. So we have to monitor when end of conversion goes low. We are using jump bit instruction. For some period of time, it will be low. After that, it will be high. That case, we have to use jump no bit instruction to monitor end of conversion signal value. Okay. Any doubts here? So we have to wait till end of conversion becomes 0. Here we have to wait end of conversion becomes 1. So after that, your conversion process is over. Suppose your end of conversion is high means your conversion process is over. So we have to enable your OE pin, that is set bit P3.0. Next, again you call delay. Now your conversion process is completed. Next step, we have to move the data from P2 because your data will be available on P2. Okay. So next move A, P2. So next clear your P3.0. So disable your output enable pin and next complement A. So this complement is for output pins are active low pins. So to get a original value, we are complementing the accumulator value and 8 LEDs are connected to P1. So move the accumulator value to A and repeat the process from here. So first channel selection, and make ALE low and ALE high and start high, ALE low, start low, and keep monitoring your end of conversion. So this instruction is for monitoring your P3.6 is equal to 1. Suppose if it is 0 means the condition is false, so it will execute the next instruction. So this instruction monitors P3.6 is equal to 0. Okay, suppose if it is 1, it will execute the next instruction, which means that your conversion process has been completed. We have to transfer the data from output pin to your P2. Okay, so enable your output pin, call the delay routing, and move your P2 content to accumulator. So the output pins are active low pins. To get the original data, I am complementing the accumulator and move that value to P1 and repeat the process. Any doubts regarding this? Students, any doubts? Please respond.
Ma'am,
Yes.
and why we are complementing A, ma'am? That one.
Actually, your output pins here, please look at the circuit diagram. So these pins are active low pins. So active low pins na 0 na 1 and 1 na 0 irukkum. புரிஞ்சுதா? Balameenakshi, active low na enna? Active low na, suppose if you are getting 0 value means that is inverted. அப்ப 1 ன்னு இருக்கும். FF na I am getting அப்படின்னா உங்க answer 0 0 ன்னு இருக்கும். So that is not a original answer, no. So I am taking one's complement to get a original data.
Yes.
Any doubts, ma'am? Okay. So let's execute this code. So this is for your P2 IO input configuration, and end of conversion pin is high to configure this pin as an input pin, and clear ALE output enable and start pins. So these three are important control signals. Okay, and next these three instructions are used to select your channels. So these instructions are used to clear 3.2, 3.3, 3.4 zeros. So channel 1 is selected. And next, make ALE high, call delay, start pin high. Similarly, after that, make ALE low, start pin low, and monitor end of conversion. If end of conversion is equal to 1 means your conversion process has been completed. After that, enable output pin to extract data from ADC, call delay for extracting data from your output lines, and the data will be available on P2, move that P2 to accumulator, and clear your P3.0 to clear the output enable. And next, complement accumulator to get a original data, and in order to view your output, move that accumulator content to P1. Okay, so this is about your delay. So I'm going to load this hex file. So let's simulate this circuit. So let's see what is happening. Suppose your input is 0, for example. So input is 0. See, here I have connected on DC voltmeter to measure the voltage at this point, channel 0. Okay, so now input voltage is 0. So none of the LEDs are glowing. Okay, so let me go to the maximum value. Maximum voltage is 5 voltage. Okay. So what is the value? Please find out. 5 voltage. So approximate value we are getting. Okay. So all the LEDs are glowing. Okay. Suppose middle value 2.80. So the calculation involved here is first decimal 2.8. Okay. So 2.8 divided by your maximum voltage 5. So 0.56. Multiply this with your size of your ADC, that is 2 power 8. 2 power 8 is equal to 256. Okay, multiply this value with 256. 4143. So this is the decimal value. So the calculation (2.8) So 2.8 divided by 5 into 256. We'll find out the value. What is the value? 143. So approximately 143. So convert this value into hex. (143) into hex, 8F. So this is the converted value. So here 1.0 from this direction, 1.0 to 1.1 F, and again, so this bit is 1.7, so F8. So the value is 8F. So write it in the reverse order. 1 0 0 0 1 1 1 1. 8F. Okay. So next, try with next value. 4.5. So find out the value of 4.5. So what is the hexadecimal equivalent for this analog value? What is the answer? 4.5 divided by 5 into 256. What is the answer? What is the answer? E5 or E6? So approximately. So 4.5 divided by 5 is equal to 4.5 divided by 5. So what is the answer? 230. Convert that value into hex, E5. So I am expecting E5. So what is the answer here? E6. Okay. But I am getting E5 here. Okay. So approximately equal to E6. So my program is working fine. Okay. So whatever value I am giving, analog value giving, so that is given to your ADC IC. So that analog value is converted into digital. So after conversion, the converted value will be available on P2. So I am going to transfer, that is I have transferred this value, converted value into P0 to visualize our output. So that's all about your ADC interfacing. Any doubts regarding this? So please note on the connections. You have to simulate this circuit and submit the input voltage. That is in the tabulation input, the volt values varies from 0 to 5. And also you have to observe the converted value, digital value. So already I have circulated the output format document. So paste your, after simulation, paste your Proteus simulation circuit and fill the table, output table. Okay. Diana,
Ma'am.
you can show that video.
Okay. Ma'am. So we have seen how we'll interface ADC0808 with 8051 in Proteus simulator. Okay, but in the previous year's lab, we'll be having an ADC0808 kit, and we'll interface that kit directly with 8051 microcontroller. And I hope you would all seen the 8051 microcontroller in your second year or subject computer architecture. I think you would have done coding with the kit. Okay, and with the same kit, this is the ADC0808 interfacing kit, that analog to digital converter. So you can directly interface this kit. This is the ADC0808 kit, and this is the 8051 microcontroller kit. Okay, you can directly interface this kit with the microcontroller kit using this bus cable. Okay, no other extra connections are required. So Ivlo Vashama, we had used these two kits to perform analog to digital conversion. Okay, so we have a conventional coding with channels and port. We'll be feeding those program in the microcontroller, and next is we'll run the code. Okay. So I think you remember all these. You have to select a start address and start typing the code. Okay, you'll type the opcodes, and after that everything is done. Then you should run the code. Okay. So this is the running method. Okay, so here see, this is the ADC0808 interfacing board, and this knob like thing is the potentiometer, okay, pot, and these are the LEDs. Okay, you'll just vary this pot and see the variations in the digital output. Okay, you have 8-bit LED and you have a pot. So to this pot, we'll be feeding in analog values. Okay, so those analog values can be measured by connecting a multimeter into these knobs. Okay, so let us see that. So this pot will be like a knob. You can change it. You can change from 0 volt. The minimum voltage is 0 and the maximum is 5 volt. So there are 3 knobs here. So you can connect the multimeter or probe irukkulla. You can, if you touch the probe in these knobs, you can find the equivalent analog voltage like 0 volt, 1.08 volt. So now they are kept the analog voltage to maximum, that is 5 volt, so that they have got the value as FF. Okay, all LEDs are glowing. So this is the reset button. Okay, so once the analog value is set, then we have to press this button so that we can get the digital values in this LED. So you can directly fill the output table with the input analog values and the output digital values. Ma'am?
Students, any other doubts regarding circuit design and your coding part? So if possible, you can try the assembly code, that is, try the ADC code in embedded C. Okay. புரிஞ்சுதாப்பா? ஏதாவது டவுட்ஸ் இருக்கா ஸ்டூடெண்ட்ஸ்?
எல்லாரும் சேம் வேல்யூஸ் ஆஃப் அனலாக் அண்ட் டிஜிட்டல் அவுட்புட் வைக்காதீங்க, ஒவ்வொருத்தரும் தனித்தனியா யூ டேக் த அவுட்புட்.
The variation from 0 to 5. Okay. So embedded C try பண்ணீங்கன்னா I will give a 5 marks extra for this experiment. Any other doubts? Okay. Shall we close, Daina? Dhanalakshmi?
Yes, ma'am.
Soundriya irukangla? Soundriya, Murali? Shall we close?
Yes, ma'am.
Yes, ma'am. Okay.
Yes, ma'am.
Okay, thank you, students.
Thank you, ma'am.
Thank you, ma'am.
Thank you.